Now that we have learned about the condition that is needed for the positive feedback amplifier to work as an oscillator, we'll take a closer look at that condition and try to find out if that is enough. So what is the condition that is needed for the circuit to work as an oscillator? The condition that we have found out is that the factor 1 minus a beta should be 0, and that we stated like this, that the product a beta should be 1. Now what does that mean, that product a beta should be 1? The is the product of the gain of the basic amplifier and the feedback factor of the feedback network beta. Now gain of the basic amplifier, it can have both the magnitude and the phase angle. Because there are capacitive elements in the amplifier, the output signal of the amplifier are usually not in phase with the input signal. There are some phase differences between X0 and Xi, the output signal, and the input signal. So the gain A, which is the ratio of X0 and Xi, usually have a phase angle along with the magnitude. So gain A will be a complex quantity, not just a pure number. It can have both the magnitude and the phase angle. And same is the case for the feedback network. It can have both the magnitude and the phase angle. So as a whole, in general, the product A beta can have both the magnitude and the phase angle, not just the magnitude. Now what happens if the product A beta also has a phase angle along with the magnitude? Let's say magnitude is 1, but it also has some phase angle, non-zero phase angle. Then what will be the result of this 1 minus A beta? Since A beta is just not 1, it has a phase angle as well, the result will not be 0. And when this result is not 0, the gain will not be infinite, the gain with feedback will not be infinite. And since the gain will not be infinite, you will not get a sustained output with 0 input in that situation. For the gain to be infinite, this has to be 0, and only then you can get a sustained output without any input signal. And for this to be 0, the product A beta must be a real number. That means its magnitude not just 1, it should also have a 0 phase angle. There it should be a real number. So that we can express like this, that the loop gain L, which is product A beta, should have a magnitude 1 and 0 phase angle. So that is how the condition we can state, and this is the necessary condition for this feedback, positive feedback amplifier to work as an oscillator circuit, that it should have a unity magnitude, the loop gain magnitude should be unity, and should have a 0 phase angle. So the necessary condition for the oscillation is broken down into two conditions. One is that the magnitude of the loop gain should be 1 and the phase angle should be 0. And these two together, they are known as the Barkhausen criterion, after the scientist who first worked on this and developed the conditions for the circuit to work as an oscillator circuit. So the final conclusion that we reach, that it's not just enough to have a unity magnitude, also we have to ensure that when the signal finishes one loop, on complete loop, the phase angle is 0. So but since the signal is going through the basic amplifier, it experiences some phase angle, there will be some phase difference, and now that goes through the feedback network, and there should be again some phase difference. so that the total phase difference as it goes through finishes one loop is 0 degree or 360 degree. So we need a shift of phase of the signal in the feedback network as well to ensure that the total phase shift is 0. Since it's most likely that the signal will experience some phase shift in the basic amplifier, and so the signal must also experience some phase shift through the feedback network so that the total phase shift is 0. So the function of the feedback network here is not just take a sample of the output signal, it should also cause some shift in phase of the signal x naught so that the total phase shift is 0. And that phase shift, to cause that phase shift, the feedback network should have some reactive element. You cannot have phase shift with the resistive element. You must have reactive element like capacitors or inductor along with the resistive element. So that is one major difference between the negative feedback amplifier and the positive feedback oscillator circuits. In negative feedback amplifiers, you don't need to have a phase shift in the feedback network. Feedback network are mostly comprised of the resistive elements, but in the oscillator circuits, feedback network cannot be just resistive with just resistive elements. They should also incorporate some capacitive or the inductive elements to cause a phase shift. Now this phase shift depends not only just the reactance of the reactive element, it will also depend on the frequency of the signal. So for different frequency, you will have different phase shift. But in order to have the total phase shift 0 or 360 degree, there will be most likely only one frequency of the signal for which this condition will be satisfied. So with the feedback network, by choosing appropriate values for the circuit elements, you can fix the frequency of the signal for which that condition will be satisfied, for which the total phase shift will be 0, and you will get a sustained oscillation. So feedback network here, it provides the two purposes. One is to make the magnitude of the product 1, and also to have a total phase shift of 0 degree or 360 degree. And so the feedback network here it has a different name. It is called the frequency selective circuit, because by varying the components of the feedback network, you can also vary the frequency for which you get the oscillation, or for which the frequency for which the phase shift will be 0. As you vary the signal, the circuit component of the feedback network, the frequency for which the phase shift will be 0 will also vary. And that is how you can use this feedback network to fix the frequency of the signal that will satisfy the Barkhausen criterion. And that's why in the oscillator circuit, this feedback network is called the frequency selective circuit. So that is our final diagram for the oscillator circuits. You have a basic amplifier, and then you have a frequency selective circuit as a feedback network that will take a sample of the output signal, produce a feedback signal XF with necessary shifting in the frequency, and that goes into the input of the basic amplifier. XF becomes XI, since product A beta will be 1, the magnitude will be 1, and the phase angle will be 0. So that is Barkhausen criterion is whenever it is satisfied in this structure, this will work as the oscillator circuit. It will produce a sustained oscillation at the output. Now, through the basic amplifier, you can have different phase shift at the output of the amplifier. But the two situations we frequently encounter in the amplifier circuits, one is this with positive gain amplifier, the other with the negative gain amplifier. With the positive gain amplifier, the shift in phase is 0, and in the negative gain amplifier, phase shift is 180 degree. So we'll just discuss these two special situations, what happens in these two cases. Positive feedback, positive gain amplifier, like we know as the non-inverting amplifier that has a positive gain, or the common base amplifier that also has a positive gain. So if we have a positive gain amplifier, then the phase shift through the amplifier will be 0, or we can say 360 degree. Now the frequency selective circuit then should not provide any phase shift in the signal. The phase shift through the frequency selective circuit should also be 0 or 360 degree, so that total phase shift remains 0 and 360 degree. So that is the situation with the positive gain amplifier, that you have 0 degree phase shift through the basic amplifier, and you should also have a 0 degree or 360 degree phase shift through the feedback network, and that is how the circuit will work. The other situation is with the negative gain amplifier. Here you have the basic amplifier with a negative gain that we have with the inverting amplifier configuration, or also we can have with the common emitter amplifier. They both have negative gains. Negative gains means that you have 180 degree phase shift. So signal will experience 180 degree phase shift as it goes from input to the output. Now the frequency selective circuit should also provide another 180 degree phase shift in this case, so that the total phase shift is 0 or 360 degree, as the Barkhausen criterion needs a 0 degree phase shift, or 0 degree for the phase angle of the product A beta. So the total phase shift we need to be 360 degree, 1 degree phase shift through the basic amplifier, and another 1 degree phase shift through the feedback network, and thus making the total phase shift 360 degree.